This week we're going to talk about two other types of graphs. First one, we'll learn how to construct a minimum cost spanning tree. And the second will be called an order requirement graph. So first, let's talk about minimum cost spanning trees. First, we need a couple definitions. A tree. A tree is just a connected graph with no cycles. So it's an acyclic connected graph. So an example, something that's a tree, could look like this. Something like that is a tree. Notice there are no cycles and it's all one piece. You can even make other trees out of this. You can just keep adding things that look like branches to it. There's another example of a tree. Now what we're going to do is find something known as a minimum cost spanning tree. And in particular, we need to know what we mean by a spanning tree. Definition. A subgraph. So a spanning tree is going to be contained in another graph. It's going to be a tree contained in another graph. And it's going to hit all of the vertices. So it's a tree inside a graph that hits all the vertices. So slightly more formal, a subgraph that is a tree that contains all vertices of the original graph is called a spanning tree. Called a spanning tree. It spans the graph. I guess I'll mention now, in case you did not notice, I'm using a whiteboard now instead of a chalkboard because, well, I have both in here. And chalkboards, well, it's hard to breathe in a room when you're using a chalkboard for a couple hours, especially when there are no fans on. And I can't have a fan on during this because the microphone picks it up and it's too loud. So let's look at some examples of spanning trees. Let's look at examples of things that are spanning trees and let's look at one example of a spanning tree and several examples of things that are not spanning trees. Because our goal here is going to be to find some spanning trees, and we want them to be minimum cost spanning trees. So let's look at this graph. So there's that. I should probably draw it a little bigger. That's okay. So we'll have 8 vertices that look like this. And we will attach that, and we'll label them A, B, C, D, E, F, H, and G. So given this graph, I'm going to construct a couple things inside it that are not trees and that are not spanning trees, and then one or maybe two spanning trees. So right here, this is a tree, but it's not a spanning tree. So the wiggly lines are a tree contained in that graph, but not a spanning tree? It's a tree because you'll notice it's all one piece. All the lines are connected somehow. There are no cycles inside that wiggly line graph. But it's not a spanning tree because it doesn't hit that vertex. Now, in these other drawings, I'm not going to label them as carefully as the first one. I'm just going to draw the lines like this. So here, same thing, same vertices. Right here, this those wiggly lines. Notice they do hit all of the vertices, but we have one piece down here and another piece up there. So it does span the vertices, but it's not a tree. So therefore it's not a spanning tree, because a spanning tree must be a tree. So it's not a tree since it's not connected. That says connected. Let's look at another. I'll draw it on the first board. So right here, same vertices that are not specifically labeled, they are the same. We'll use the same vertices. So right here, let's look at this. That right there. I don't like that example. Sorry. It'll illustrate the same thing, so you can, if you want, you can leave that there. Let's throw this one in. Okay. So right there, the wiggly lines, notice they do hit all the vertices, so it does, this subgraph that we created with wiggly lines does span the vertices. But right here, it has a cycle. So not a tree, since it has a cycle over there. In the first one I drew, the entire thing was a cycle, and I didn't want that to be the example. And let's look at this. Which ones do I want to include? Let's do this. Right there, those wiggly lines, they hit all of the vertices. There's also no cycle, because it just looks like, what, that. That's not a cycle. And it hits all the vertices, so that right there is an example of a spanning tree. A tree, meaning no cycles and all one piece that hits all of the vertices. And there are multiple examples of spanning trees in this. I mean, you could probably just come up with one just going in another direction. So like this. There. As you can see, I decided to stop doing wiggly lines. But you can make several different spanning trees on this. It's a spanning tree if it hits all of the vertices. And what we'd like to do, so we just had a graph here. We could assign values to those edges, or weights to those edges. And then one question you could ask is, can we find a spanning tree of minimum length? Minimum cost, I should say. Or length, if the cost measure length. Can we find a spanning tree of minimum cost? And the answer is yes, we can. So when we were trying to find a minimum cost Hamiltonian cycle, the answer was not necessarily yes, but we did have algorithms that could help us. Given a graph, can you find a minimum cost Hamiltonian cycle? Very difficult question in math. Given a graph, can you find a minimum cost spanning tree? Has an answer. And it has an algorithm that goes with it, and it's not even all that complicated of an algorithm. I actually think it's a much easier algorithm to deal with than the two we did last week, although maybe I'm wrong about that. So let's look at an example. Example. The graph gives links in a cable TV network. So most of you students probably too young to know what cable TV is. TV used to come in through wires. I don't know much about it either. All I know is now it's different. I think there's a cable thing somewhere in this room. Over there, there's a cable thing. I don't have cable. This graph gives links in a cable TV network and provides costs to create each link. So let's get rid of that period. So right here, I'll draw it here. This is going to be illustrated by a complete graph because we can create links from any one port to another. Right here, we're going to have points where the cable can stream from one point to another. I don't know if stream is the right word for cable. Cable can connect from one place to another. So here's the graph. Now let's put values on these. 7, 8, 16, 13, 12, 14, 5, 6, 15, and 9. So to create a cable connection from, say, C to D costs 9 units of whatever money we're using, dollars. And the question is, so right here, well, before we get to the question, if you want a connection from, say, A to C, you don't necessarily need this $13 connection. Maybe there's a better example to it. Well, you don't necessarily need a $13 connection. You could connect from A to B and then B to C, and the cable can go from A to B and then from B to C, and therefore it can connect from A to C. So you don't necessarily need a direct connection in order to go from one place to another. You could go through a third place, an intermediary place. So right here, what we want is to cover all 5 of these points. And we want to do that at a minimum cost. So goal. Provide service to between any pair of locations at a minimum cost. So right here, what we want is a minimum cost spanning tree, because if we have a tree that hits all the vertices, then we'll be able to connect any one to any other. Now, how can we find a minimum cost spanning tree? You might be thinking of a way you can do that similar to the sorted edges algorithm. You might think you can put these edges in order of increasing weight, start at the cheapest one, 5 in this case, and just add them on until you get an appropriate tree. And that's right. That method actually does give us a minimum cost spanning tree. So I'll write that algorithm down and then talk about it a little. It's known as Kruskal's algorithm. Kruskal's algorithm. Add links. Kruskal's algorithm to find a minimum cost spanning tree. So to find a spanning tree of minimum cost. Add links in order of cheapest cost so that no circuits form and so that every vertex, the book says every vertex belongs to some link added. I'm just going to say so that every vertex is hit. We're creating a tree by starting at the lowest and going up. So to do this, let's first rank these costs. Well, maybe Kruskal was a mathematician in the 1900s. He came up with his algorithm sometime in the 50s or 60s, I think. And when he proposed it, he wasn't positive it would definitely give, well, when he first thought of it, he wasn't positive it would definitely give a minimum cost spanning tree. Just like in the sorted edges algorithm, I mean, there's really little reason to think that would definitely give you the minimum cost Hamiltonian cycle. This is a very similar argument, and so you might not expect it to definitely give a minimum cost spanning tree. But he did prove eventually that it does give a minimum cost spanning tree. And that was a pretty large result. One of the larger math results in the last, say, 70 years. I think he did it about 60, 70 years ago. So let's rank these costs. I'm just going to do it over here. 5, there are going to be 10 numbers, so let's make sure we have 10 numbers. 6, 7, 8, 9, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 10. Yes. So let's add them on. And the only violation is if we create a cycle. Or if we go beyond making a tree, I guess. So you stop this algorithm once you hit all the vertices, and it's connected. So we'll start by adding the cheapest. Then we'll add the next cheapest if we can. That doesn't produce any cycles. But look what happens if you add 7. If you add 7, there's a cycle. So you can't add 7. That would be, in terms of these cable connections, that would be a waste of money because it's redundant. You can already connect to A to E by routing through D. So we don't need this one up here. What about 8? Yeah, okay, that brings us somewhere we haven't been. So that's good. What about the next number? 9. Here. That doesn't create any cycles. Now right here, we're actually done. Because we have a connected thing that hits all the vertices. So we didn't even have to consider 12. You consider 12, that's redundant. Because we already can connect B to E. It's actually a cycle. It's a relatively complicated cycle. But you can see that if you connect that, it looks like that's actually a cycle. And think of this as like untwisting that so that it just becomes a rectangle. That's not a rectangle. I see that as a cycle. There are probably a few ways you can see it. Grab the top, grab the bottom, twist one of them around so that it just becomes a rectangle. So that is a cycle if you add 12. If you add 13, that's also a cycle, makes that triangle. Add 14, makes that triangle. Add 15, makes that triangle. Add 16, makes that trapezoid, so that's a cycle. So right here, we've constructed a minimum cost spanning tree. And was the goal to find the cost to actually, yeah, okay, so we'll answer the cost. There's the spanning tree. And the cost is whatever those numbers added together is. Cost equals 5, let's do them in order, plus 6, plus 8, plus 9. Are those the right numbers? Yeah, so 5, 6, 8, and 9. A lot of ways you could add them together. 11 plus 9 is 20, plus 8 is 28. The first way I saw it was actually 14 plus 14, because that's like a symmetric addition. It's always nice to look at shortcuts for addition. And going in order here, that's actually easy to make a mistake if you go in order, because 11 plus 8 is 19. 19 plus 9 is 28. That's much harder than 20 plus 8, I think. So this cost to create this cable network that spans all of these nodes is 28 units of whatever. Let's look at another example. So one other type of thing you could do here is, say you are an ambulance, and you want to get to a bunch. You want to be able to get to a bunch of different houses in your area. Hopefully, that's every house in your area. Well, you can do that by making a path. A path from your ambulance place to any house, and you want to do that in minimum time. Well, the given network, you would want to create a tree that hits all of the houses you want to hit. And you want to do it at the cheapest cost, in this case time, because ambulances probably want to get places as quickly as possible. So let's consider the following road network with the following costs, and we will assume these costs are time it takes to use a certain road. And we'll simplify this road network a little. There's a scratch on this board, so that might show up there. So here's this road network. Every one of these is going to be some place to get to. I'm not going to label them with letters because that won't be useful. Won't be necessary, let's say. That's a better word for that. So let's call this one 1, this one 10, this one 4, this one 6, this one 4, this one 3, 5, 11, 1, I'm trying to do this sideways because Sorry, 4, not 1 there. 3, 7, 2, 8, 3, 1, 1, 4, 5. So in that first example, it was relatively easy to find when a cycle was created. In this one, it might not be as easy. But we're still going to want to construct a minimum cost spanning tree. So again, we're going to use Kruskal's algorithm. So let's label the sides in order of increasing cost. Notice here there are repeats. We didn't have repeats in our other ones. 1, 1. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 17. Remember, that's a lot of numbers. Let's make sure we get all of them. 1, 1. I see 1, 2. I see 3 3s. I see 1, 2, 4 4s. This example is from the textbook. 4 4s. I didn't notice this in what I wrote before because I didn't actually list them in my notes. 4 4s, 3 3s, 1 2, and 2 1s. Very poorly set up. So I'm going to change this from the textbook a little. This one that I didn't want to label 1 before, I'm going to call that a 2. So I'm changing that one to a 2. So I'm changing that up there to a 2. I apologize if you are erasing. It's actually not going to make a difference in the final answer. So if you don't want to scribble out or erase, don't have to. But now look how nice that looks. 1 1, 2 2s, 3 3s, 4 4s, and so on. 5s, there are only 2 of. We can change a bunch of the other ones to 5s if we want. 6s, there's a 6. There's a 7, and a 10, and an 11. 1, 2, 3, 4, 5, 6. I missed a number. Where did I miss a number? You probably see it right in front of me. 8. Right in the middle. Okay. So we're going to add these edges as long as we can until all 12 vertices are connected. 1. That's okay. 2. Now when doing this, you could choose either one you want as long as it doesn't violate the algorithm or it doesn't create a tree or a cycle. So I could have started down there or up there. 3. Well, that's okay. That's not going to make a cycle. That doesn't make a cycle. That doesn't make a cycle. 4. There are 4 4s. That's okay. That's okay. That didn't create a cycle, did it? Nope, no cycles. That's okay. That didn't create a cycle. And that's okay. None of them created, that did not create a cycle yet, but notice, it is all connected, but notice we have not hit this vertex yet. So we added all of these so far. What about the 5s? Well, you add this 5, that makes a cycle. You add this 5, what does that do? That does not add a cycle, does it? Oh, no, that does. Yes, it does. That makes a cycle. If you add this 5, you see, you have to take a step back sometimes at these and see if you see a cycle. Because with extra vertices, it might not be obvious. So it creates this cycle, this L-shaped cycle. So we'll not add that other 5. What about 6? Well, yeah, 6 will give us the last edge. Add any of these others, and it'll make a cycle, that'll make a cycle, that makes a cycle, and that makes a cycle up there. So we add all of these numbers together to find the cost. And what do we get? 10, 22, 31, 36. Probably many better ways of adding that than that. So 36 is the cost. Since I changed a 1 to a 2, the answer in the book is probably 35. I didn't write down the answer. Just looking at the path to see if it's the same path I made. Yes, it is. So I have cost of 36. So right here, we followed Kruskal's algorithm. We did not add an edge if it gave us a cycle, and we got the total cost.